Today's speaker is Dr. Tevong from CERN and University of Cambridge. And the title is U Positivity Bounds on Effective Field Theories. So please begin.
Thank you very much for that introduction. And the paper on which my talk will be based is this reference here. So I encourage you to look there for more technical details. And there's some fantastic results there with Scott and Joe DeVigi, both at Cambridge. So the title is New Positivity Bounds, but most of what I will talk about is assuming that you haven't heard or gone through any of the positivity bounds that have been a fairly hot topic recently. There's been many papers on the subject. So I'll try and give a introduction, in a sense, a derivation of these positivity bounds from first principles, and in the process show how we obtain new ones for the case of massive spinning particles in effective field theories. So please feel free to stop me with any questions along the way as well. I think I'll try and be relatively informal in presenting this. So this is also something that I learned from the expertise of Scott, who's done a lot of work on this subject before. So I'll be happy to discuss any of the further technical aspects of these offline if you'd like to know more about some of these things, because I realized actually that in an hour there's not enough time to really go in all the subtle aspects of these positivity bounds. The main takeaway I want to give is why effective field theory is an important framework. So I'll start with motivating the general framework of effective field theory and how Wilson coefficients provide us with a connection to the UV from an IR point of view, where we can capture the phenomenology, but also aspects of the theory in the UV without having direct access to what that theory is. So this motivates the positivity bounds on these Wilson coefficients, where I will then derive these positivity bounds and in particular do so in the more general case of massive spinning particles, where, as I mentioned, there are more subtle technical aspects that one has to take into account compared to the scalar or massless case that is typically considered in the literature. And then finally, I'll just give a brief example application to spin a scalar scattering with a dimension 7 operator before concluding. So the effective field theory framework can be written schematically as the following Lagrangian. We have not only a renormalizable set of operators, but also the higher dimensional operators beyond dimension 4. So the previous point of view up until the 1960s was that the way for a quantum field theory to be sensible and to make sense was for it to be renormalizable with a finite number of parameters. And this is why theories like QED were considered fundamental in a sense, because it was renormalizable with a finite number of parameters. But we now know, thanks to Weinberg and Polchinski and Wilson and others, that actually the modern point of view is that the success of our quantum field theories are really due to them being effective field theories. In some sense, all of our quantum field theories are effective field theories, where the higher dimensional operators are there. And the almost totalitarian principle is that all operators, including all combinations of fields that are allowed by the Lorentz and gauge symmetries and other symmetries that one puts into the theory, all of them have to be included. So the reason for the higher dimensional operators not being seen in some sense is that they are suppressed by the scale of the cutoff of the theory, up to which the theory is considered to be valid effective field theory at low energies. This makes sense of lots of puzzles at the time, such as accidental symmetries. Why were some symmetries fundamental and some appeared to be only accidentally globally respected? And this is because the accidental symmetries are byproducts of all the possible combinations one can write down up to dimension 4, just happens to preserve some accidental symmetries. So all of this is a fantastic way of understanding essentially the reason why the theory seemed to be organized the way it is. And in fact, we've always been doing effective field theory, even before we knew what an effective field theory was. So by this principle of writing down all the possible combinations of fields that is allowed by the symmetries, then really the successful QED theory at the time should also have included the combinations at higher operator dimensions, which was independently discovered as Fermi theory and the Euler-Heisenberg theory in the 1930s. But really, we know this is part of the QED effective field theory, where we include all the combinations of 4 fermion operators and all the combinations of 4 field strength operators. So these would be dimension 6 and dimension 8 operators, respectively, by counting the mass dimensions. And the EFT data is indirectly sensitive to whatever UV completes this EFT by looking at the phenomenology of these coefficients. And this is what established the V minus A structure of this 4 fermion dimension 6 operator, for example. And we now know that the standard model is a UV completion of this particular EFT. This nonlinear light by light scattering that is predicted by the Euler-Heisenberg dimension 8 term is something that's only been seen in the last few years, actually, in heavy ion ultra-peripheral collisions at the LHC, where they measured light by light scattering for the first time. So the Wilson coefficients are the key players in these positivity bounds that I will talk about. So they are generated by integrating out the UV physics that would give a relation between these coefficients and the specific model that is responsible for them. So the picture is as follows. Below the mass of the W, we have this effective QED theory, and in fact, it should be an effective weak theory. And this contains a Fermi theory and the following interactions in the EFT, the 4 fermion and the dimension 8 light by light interaction, for example. And at the time, the UV completion was unknown at some scale, at some higher energies. That was at the time the high energy frontier of tens of GeV. And after the W, the Z, the top, and the Higgs boson discovery, and so on, we now know the UV theory is a standard model, and the UV completion is the following diagrams, which generate these coefficients from the exchange of heavy W bosons and from the loop diagrams involving the standard model fermions. Now, the philosophy of the effective field theory says we have to write down all the possible operators. So the standard model is really a standard model effective field theory where we have these higher dimensional operator terms. And Weinberg in particular, in a sense, predicted neutrino masses from the famous Weinberg operator, which is a unique dimension 5 combination of standard model fields, which when the Higgs gets a vacuum expectation value gives neutrinos masses. And then the leading CP even conserving term is the dimension 6, lepton number conserving operators would be at dimension 6, followed by dimension 8. And at dimension 7, we would have a lepton number violating operator. So the question now is, at the TeV scale or higher, what is the UV completion? So we already, in a sense, have a hint, potentially, from the famous B anomalies that there is a 4 fermion operator in the standard model that seems to deviate from a 0 value, indicating a possible sign of new physics in these Wilson coefficients. This is the famous B2K meson decay, which would be mediated by this BS to mu mu interaction, this 4 fermion operator. And for example, a possible concrete UV completion that could generate this is the exchange of a Z prime or some scalar or vector leptoquark by these 3-level diagrams. Or it could be a combination or loop diagrams and so on. And this is potentially very exciting if true. We want to take, though, a more general point of view of what the UV completion could be without specifying a specific model. So without writing down a UV Lagrangian, without saying what the particle content is, and without even specifying whether it could be even a non-traditional quantum field theory that is deformed in some way that we couldn't even anticipate. So from this point of view, in the IR, we want to be sensitive to certain properties of the UV theory from a general point of view, where we don't go systematically UV completion by UV completion, adding a Z prime network quark, adding a specific gauge forces and so on. If we just have access to the EFT and we measure the higher dimensional operator coefficients, for example, 2-dimensionate operators with coefficients C8 and C8 prime, and experiments tell us that they can measure their values such that they have to lie within this ellipse, then of course you can always match to an explicit model and say, well, my Z prime or my new physics predicts this particular value in this space and is now allowed. If it predicts something outside, it's not allowed. And this is a way of matching to the UV from this IR information. Positivity bounds provide a very interesting complementary and different approach to this. This uses the fact that if the UV completion is unitary, local, and causal, then we can say in complete generality, just assuming these principles, that the coefficients have to be positive in some sense. So schematically, this would say, without having to specify the UV theory explicitly, that the coefficients have to live in this space. And if they live in this space, then say the experimentalists shrink their ellipse and measure even more precisely and find that it lives in this region here, then this would be revolutionary in the sense that it's really telling you that the UV completion has to violate either unitarity, locality, or causality. And this would be a quantum field theory that would be very difficult to make sense of. So in some ways, these bounds are a theoretical prior that restrict the allowed space, but they can also be seen as a way of getting information that might point to something even more radical than conventional UV completion. So to derive these positivity bounds, I will now sketch essentially the way that we are sensitive to these UV properties. And it's really simply using the residue theorem of complex analysis. So this is simply isolating the coefficient of interest by the residue theorem that tells you that the coefficient of the simple pole in the Laurent expansion of some general function f of z, if this is analytic in the complex plane, then we can isolate the B1 coefficient here of the simple pole by doing a contour integral around the pole. So not only can we choose any contour we like from analyticity of this function, we can always deform the contour to any contour that we like from C to C prime to isolate this contour. This is essentially the property that allows us to take an amplitude, analytically continue it to the complex S plane, where S is the Mandelstam variable for the center of mass energy squared, and deform that contour to be sensitive to high energies, that is then sensitive to the properties of this amplitude at large S. So this is what we essentially do, starting from the amplitude as a function of S and T, where S and T are the Mandelstam variables. And these positivity bounds basically apply to any 2 to 2 amplitudes which I write here in the general 1, 2, 2, 3, 4 case, but will restrict to the elastic case where particle 3 has to be the same as particle 1 and particle 4 has to be the same as particle 2, because that's where the positivity bounds will apply. But in general, the properties of an elastic 2 to 2 amplitude, where the particles have helicities, H1, H2, H3, and H4, is defined by this transition matrix element, where T is the transition matrix from the S matrix parameterized in the usual way. So this is well defined in the physical S-channel region, where this is something you can calculate in the EFT with your effective higher dimensional operator. And this gives you some concrete function of ST and your higher dimensional Wilson coefficients. Now we can analytically continue this function. If we see this as a function of S, we can analytically continue to complex S. And we'll call this function, this A, H1, H2, H3, H4. So we know the analytic structure of this function, since the poles are given by the mass squared of the light particles. So we assume for simplicity here, though we can generalize this, that all the light particles for 1 and 2 and 3 and 4 have the same mass m. So the pole in this amplitude will be at the single particle threshold, and we'll have a branch cut at the 2 particle threshold, since this can introduce, for example, loop diagrams where we get logs and so on. So we know that along the real S-axis, we will have a pole at m squared and a branch cut from 4m squared onwards. And when we analytically continue this function to complex S, the way we make sense of the negative S values is that this can be related to the physical U-channel amplitude. So along the negative S region, this can be related to essentially this amplitude, which is the U-channel process, where we have a 1 and a 4 bar going to a 3 and a 2 bar, where the bars denote the helicities are the opposite helicities. So the physical U-channel region for the U-channel amplitude is the negative S values, or positive U, and is defined by this transition matrix element. And again, we can also analytically continue this to complex U, or equivalently to complex S. So the poles and branch cuts in this U-channel amplitude gives on the S plane, complex plane, along the real axis, the negative real axis, a pole at 3m squared minus t and a branch cut from minus t onwards. And crossing symmetry will relate the amplitude H1, H2, H3, H4, the S-channel amplitude, to this U-channel amplitude. So now we know how to analytically continue this function. There's one more subtlety that is important to take into account for the general spinning case, which is that to be able to analytically continue these functions and deform the contour of this function, we know where the poles and branch cuts are, as I showed you before. These are the physical poles and branch cuts in the amplitude. But we also have kinematic singularities in amplitudes beyond the scalar case. So what we'll really be working with is this function A hat. This A hat function is nothing more than the amplitude that I talked about, multiplied by this K factor that takes into account and removes the kinematic singularities that arises in the cases where the spins of the particle S1, S2, and their helicities H1, H2 are denoted by these exponents here. We multiply by this factor because in general, if you calculate an amplitude for the spinning case, they will come with additional singularities due to the polarizations of the particles involved. And these singularities due to polarizations in a sense, get in the way of the analytic structure of the function that we want to deform the contour. So by multiplying by this k factor, we have a nicely behaved analytic function where the only poles and branch cuts are the ones that I mentioned on the previous slide. Okay, so this is essentially how we set up our what's known as dispersion relations. The amplitude in the EFT that you can calculate, as I mentioned before, you can take a concrete Lagrangian in an EFT and calculate a 2 to 2 amplitude. And this will be a function of S and T and include the dependence on higher dimensional operators, so the dependence on the Wilson coefficients. And the derivatives in S of this amplitude that you can calculate give you the Wilson coefficients. So in general, for example, dimension 6 operator will enter multiplied by a power of S, and a dimension 8 operator will enter multiplied by a power of S squared to compensate for the 1 over lambda squared and 1 over lambda to the 4 that the coefficients enter with. So by choosing different values of this capital N here, and taking the derivative of these amplitudes, these regulated amplitudes, the A hats, this gives us some expression in terms of the Wilson coefficients. Now this can be related to the contour integral that isolates these coefficients, just like in the complex function I gave before. So we can take a point within the EFT field range, S0, where S0 is less than the cutoff of the theory, and deform this contour again to very large S values. So we deform them around the branch cuts, and this C prime contour goes out to even to infinity if necessary, at which point it is sensitive to the UV properties of the theory, because we can separate this contour into 3 parts, one of which is this IUV, which is the part of the contour integral that is the big circles at infinity, or at the UV scale. And then we have the IS, which is the parts along the real axis, which is known as the discontinuity across the branch cut, or in older terminology is known as the absorptive part of the amplitude, and similarly across the U channel here. And it is the fact that we deform this contour to these large S values at infinity that gives us the sensitivity to the UV properties of locality for the case of these gray contours at infinity. We'll see why that is sensitive to locality, and unitarity for the parts that are related to the discontinuities across the branch cut. And the name of the game is to show that this vanishes and these 2 contributions here are positive. Can you see my mouse?
No.
Nope. Okay. Maybe I was pointing at the wrong screen. So can you see it here?
Yes, I can.
Okay, sorry about that. So these 2 contributions here can be shown to be positive, or actually more generally, they are not always positive. And if they're not positive, they're known as sum rules. But if one can show that these 2 contributions have to be positive, and that this contribution vanishes by locality, then this means that the left-hand side, which is your EFT Wilson coefficient, has to be positive from the properties of the UV. Okay, so concretely, to show locality, we take the part of the integral that goes along this circle at infinity, and for large S, let's take S going to infinity, this K function that regularizes the amplitude that I mentioned before has this dependence on S, which depends on the spins of the particles and their helicities. And the amplitude has some asymptotic power that goes like s to the 2 times n uv. So this n uv is a property that tells you how fast the amplitude converges with ng. And essentially the reason why this bound is called locality is that it has been shown by Froissart and others that any UV theory that is local has to have an ng growth that is bounded by s squared. In other words, nuv has to be less than or equal to 1 for the theory to be local. Now, this is very interesting because it tells you that if you choose your n, the big N, to be large enough, then this IUV goes to 0 as s goes to infinity. So the contribution from this gray contour will vanish if n is sufficiently large relative to the NUV growth. And this is parameterized in this n hat, but it's simply restating the fact that the exponent in the denominator must be larger than the exponent in the numerator for this integral at infinity to vanish. And this is saying that NUV must be less than or equal to n hat, where n hat is this big N with the appropriate spin-dependent and helicity-dependent weightings. So recall also that this big N here essentially tells you which operator you're choosing this to isolate different operators in your amplitude. So here, this was the left-hand side, and you essentially choose how many derivatives of S you want to take. And depending on the number of derivatives of S, you'll either get a dimension 6, dimension 8, or dimension 10, and so on, operator coefficient. So what we see here is that for isolating an operator of dimension 8, this n hat must be equal to 1. And if NUV has to be less than or equal to 1, then we can't isolate, in this case, an operator of dimension 6, because this would require n hat to be a half. And if n hat is a half, then this means NUV must be less than or equal to a half. And this would then require the energy growth at large S to be converging faster than the Froissart bound. So we'd have to make an extra assumption on the energy growth, which would require an NUV to be less than or equal to 0. And in this case, it is not as interesting. But what we'll show is that there are other positivity bounds which allow you to assume a milder energy growth. So we'll show that our positivity bounds allow NUV less than or equal to a half. And this is something that requires less assumptions and enables constraints on dimension 6 and 7 operators. So we haven't finished to show that the coefficients of the higher dimensional operators can be positive. The next part is this discontinuity across the branch cut. So this IS contribution is given by the integral across the branch cut, which is known as a discontinuity, since it's taking the amplitude along the positive real axis minus the one along the negative real axis in the complex plane. We call it the absorptive part in our paper, which is just the same thing as a discontinuity with a factor of 1/2i. So this absorptive part, or discontinuity, is related to the transition matrix elements that I mentioned before. And from unitarity of the S matrix, which you'll recognize as nothing more than the optical theorem, this relates this to to the following positive definite quantity. So this discontinuity across the branch cut is then positive, and in this case, the same integral across the U channel proceeds in the same way. So what we showed is essentially that in the forward limit for t equals 0, as I said before, you can isolate the coefficients of your amplitude involving the EFT operators by taking derivatives of the amplitude. And these derivatives of the amplitude to some power 2n for 2n number of derivatives is related to a contour integral in the complex plane of the function analytically continued to high energies. And this is then sensitive to the properties at these high energies of the UV theory, where the amplitude must satisfy certain properties for it to be greater than 0. And since the scattering angle is related to t in this way, then the t equals 0 is also known as the forward scattering positivity bound. So these are the bounds that have been known well for a long time, since the 60s onwards, but has been in particular revived for modern theories by a famous 2006 paper by Arkani Ahmed and Adams, Murtazi, and so on. And since then, there's been much work in generalizing these bounds to go, for example, beyond the forward limit. So we can also derive positivity bounds for not just s derivatives, but also t derivatives. So if we take t derivatives in addition to s derivatives, we now have to show that this is positive. So locality follows through as before, but these extra contributions of the t derivatives across the s and u channel branch cuts are now in particular non-trivial for the massive spinning case. So the reason is that this t derivative can be seen as a theta derivative in the angle. And this t derivative is essentially for small theta, because in the end we'll also take theta going to 0. So we'll have to act these essentially theta derivatives on the states which have a dependence on theta. So previously in our matrix element here, we didn't really care that there was a theta dependence here. But now that we're acting these t derivatives, these two particle states for the out states have to be rotated in the scattering plane by this theta angle using the angular momentum operator jy. So we take our plane to be in the x and z axis, in the x and z plane. And I define here the hs to be the difference of the two particle helicities. So the way that this is done is to do a partial wave expansion, where we convert essentially these two particle states to a sum over a single particle ket consisting of the helicities of the combined two particles, and factoring out the total momentum, spin, and helicities in this way. So this is nothing more than the Wigner-D matrices if you put in specific values of the spins. So now, when acting on the t derivative on this will bring down the factors of the angular momentum operator. And instead of having just this piece that we showed before being manifestly positive, we now have also this factor of the angular momentum squared. So this is also interesting because the angular momentum is bounded from below. So it's not only positive, but it also has to be larger than a certain quantity, which is the magnitude of the difference of the helistes. So this allows a stronger bound to be placed than simply allowing it to be positive, because it must also be larger than a certain positive number. The other aspect that is non-trivial is not just the theta dependence of the final states that have to be rotated and taken into account in the t derivative, but the U-channel discontinuity has an extra theta dependence that comes from the crossing relations when we relate the S-channel amplitude, AH1, H2, H3, H4, is related to the U-channel amplitude by these rotation matrices that depend on theta. So the rotation angle chi is some function of theta. In this case, the scattering in the U-channel plane for the U-channel amplitude. And this means when we act the t derivatives on the final states, we not only have to act on the angular momentum operator that rotates the final states, we also have to act on the crossing relation matrices that relates the S-channel amplitude to the U-channel amplitude. So this is the relation of the S-channel amplitude to the U-channel amplitude that is now expanded in partial waves. So we get this piece, which is the same as the S-channel, but we also get these two crossing matrices. And so acting on the t derivatives now gives not only the same piece that we got in the S-channel case, but we get this extra contribution here that comes from the t derivatives acting on the crossing relation matrices. So this extra piece here, which is written below, but is maybe not very informative, but it's basically just if you carry through the t derivatives acting on these crossing matrices, then you get these extra factors. The first of which is manifestly positive, since this is absolute magnitude squared of a quantity. This is not necessarily positive. So to have positivity of this t derivative across the U-channel discontinuity, we can stare at this piece for a while and notice that if we sum over the helistes, if we sum over amplitudes with helistes that add up to some HQ, then the sum of these contributions will make this positive. So this tells us that unlike the scalar case, where all the spin-dependent things become trivial and these crossing relations just become unity, or in the massless case as well, in the massless case, all these factors become trivial. In the massive spinning case, we have to take into account this extra contribution. The U-channel positivity no longer trivially follows from the S-channel positivity. One also has to be careful in the massless case that it seems like we can just take the mass to be zero and then this contribution vanishes. But there's a hidden assumption in doing so, which is that taking this mass to be zero is assuming that the amplitude contribution from the UV matrix elements, the unknown UV matrix elements, doesn't grow like 1 over m squared. And we know this is something that happens, for example, in the longitudinal modes for spins greater than or equal to 1. These will grow like 1 over m squared and require some Higgs-like mechanism to restrict this growth of the amplitude. So there is a possibility of just setting the mass to zero, but the extra assumption must be made explicit to also specify that we're assuming a UV theory in which the amplitude doesn't grow like 1 over m squared. Alternatively, what we point out is that we can still make this positive by summing over the helistes in this way, and this is what gives a general expression that is positive without this extra assumption. Okay, so this was just to sketch essentially the steps involved and how the massive spinning case requires some extra technical steps. there are other contributions from the T derivatives acting on the K regulator that I mentioned before. So I don't want to, I think I'm already boring you enough with all the technical details. So the extra steps are just to really be careful in acting the T derivative on all the pieces, including the K regulator piece, and then this piece, take into account this, and so on. But the final result is basically that our new positivity bound is the following general expression. And what this is saying is that the T derivatives acting on the 2n S derivatives of our regulated amplitude, where we just take our 2 elastic scattering amplitude and multiply by that K factor that I mentioned before. And this HU denotes that we're summing over the helicities. We're summing over all the amplitudes helicities that add up to some fixed value, HU, that we can choose. And this sum, as we just derived, has to be positive, although it depends on this combination that we call alpha. So this combination depends on the n that we choose here, on the spins and the helicities. And if alpha is greater than 0, then we get this bound that is only positive if we choose some scale mu, such that we have to add an extra piece to make this combination with this combination positive. So this is a trick that's been used before to get beyond forward limit positivity bounds for the T derivatives, which is not necessarily positive unless you add this piece, which makes it positive. But what is new in our results is that for sufficiently large helicities, when alpha is negative, we get a positivity bound that doesn't rely on adding some contribution. So this is just greater than 0 for negative alpha or sufficiently large helicities. So the reason why it's interesting that we can bound this amplitude independently of the 0 T derivative amplitude is that we don't have to make extra assumptions to get constraints at less than dimension 8. So with a milder assumption on the UV growth, in particular, we assume super Fossard convergence of NUV equal to 1/2, we can place constraints on dimension 7 operators and potentially dimension 6. Okay, so I want to end with just one concrete example to show how this machinery can be applied. So if we forget about all the derivations that led to this, and we just want to take this and apply it to some theory, then take, for example, this dimension 7 operator and calculate a 2-to-2 elastic scattering amplitude involving a spinner and a scalar with the following helicities. So this gives this amplitude, and the polarizations involved give some non-analyticities related to these polarizations. So these are the kinematic singularities that we wanted to remove. This is why we had to introduce this A hat, where we multiplied by this K factor, which for the spin half case of this spinner scalar scattering is the following. And so we see that the remaining amplitude is analytical as expected. So in this case, because it's dimension 7, as I mentioned before, we can't get a constraint on this from the forward limit positivity bound without assuming a very strong convergence, much stronger than the locality requirement. But we can assume something a bit weaker, which is still stronger than the locality requirement of Fossard, but is still strong enough to be interesting, which is requiring the NG growth to be S to the 2 NUV, where NUV is 1/2. So the NG growth is limited by S rather than S squared. And in this case, our new positivity bound applies. We can choose N to be equal to 0. And this expression here, general expression, then becomes this positivity bound, which tells us that the coefficient lambda 7 must be greater than 0, must be positive. So this is in a sense, a diagnostic of the assumption of this NG growth. If this dimension 7 operator coefficient were measured to violate this NG bound, the only way this could be so is if the NG growth of the amplitudes in the UV grow faster than NUV equal to a half. So it would have to grow at least with S squared. So this is something that tells us, for example, there must be some T-channel amplitude in the UV, because without theories that grow like S are those that, for example, don't contain a T-channel. Okay, so with that, I'll conclude with some general summary, which is the idea of positivity bounds to place general constraints on Wilson coefficients of the higher dimensional operators of an EFT is interesting because it is sensitive to these fundamental UV properties. Unitarity was the positivity across the branch cuts. Locality was the convergence of the NG growth at large S, and we can assume slightly weaker or even slightly stronger assumptions on this NG growth than the strictly far-side requirement of S squared. And causality is basically related to the fact that we could analytically continue our amplitude. This is, in a sense, a swampland criteria, but rather than being a swampland from the string landscape, this is, to me, even more interesting because it's just basic QFT principles. It's a swampland criteria from consistent QFTs. So this restriction on the space of EFT coefficients can be seen as a theoretical prior, but it can also be seen as a way to target experimentally the values of the coefficients that are sensitive to these properties. Because if we do measure a higher dimensional operator coefficient with the wrong sign according to these properties, then this would point to a UV completion that would have to be far more radical than anything that we can imagine in a conventional UV completion that is just adding particles and forces. These bounds can also improve our understanding of UV and R relations by understanding how these general connections restrict the EFT. We can make more sweeping statements about what is allowed or not allowed in our EFT coefficients. So there's still a lot more room to discover new types of bounds and new types of relations. So sorry, I didn't have time to add a comprehensive reference survey. So I encourage you to look at the introduction of our paper to see essentially a summary of all the work that's been going on in deriving these positivity bounds and generalizing them to many cases. So with that, thank you for listening. I'm happy to take any questions now.
Okay, thank you very much for the detailed, informative explanation. Questions or comments?
So I have a question. If we consider the external line as the scalar, we have similar constraint about this. I mean, when we consider the external scalar case, then the bound changes or not?
When we consider the scalar case?
Yes.
So in the scalar case, there isn't this this k function. Well, the k function just becomes 1. So
yeah.
You were asking about this k?
I mean, I'm asking that the positivity bound you derived can be used in the case of scalar case.
Yes, yes. So sorry, I didn't maybe make this clear, but the general bounds we derive are for any spins So in particular, just by setting S1 and S2 to 0 and H1 and H2 to 0, this reproduces all the known scalar bounds.
So can you show me the bound?
So in this
This
case,
one, yes, yes. And
this basically one just sets S1, S2, and HS and HU to 0. And then this is just alpha is just n, basically the choice of n, that one.
okay, so when we take S equal 1, n equal 1, then the left-hand side is the coefficient of S squared t, right?
Yes.
And I feel weird because the scattering amplitude of the full scalar, when we consider the fermion loop, then in the low energy limit, the scattering amplitude, the S squared t coefficient of scattering amplitude is negative, I think.
So in this case, there's this extra piece. And this is why this, this scale mu has to be chosen so as to make this positive, which if the mu scale is too low, then these bounds are no longer interesting. So
Yeah,
this is why.
But if we consider just 5 psi bar, then it is renormalizable, right? Then we can take mu equal infinity.
But if we take mu to be infinity,
Yeah.
then this piece will be negative. Will be sorry, this piece has to be added to this to make it positive. And if we take mu greater than.
So I can see your, I cannot see your cursor.
Oh, sorry.
Yeah.
Here it is. Okay, yes. So this piece has to be added to that to make it positive. And in the case where we take mu to be too large, then this contribution would become much smaller.
Yes.
But in this case, the scalar bound just becomes the t derivative of this has to be positive, which is just the trivial scalar case, right? But you're arguing that in the case of a scalar with a fermion loop, you get a negative coefficient.
Yeah.
Okay, well, I think I have to look at the explicit amplitude to see whether or not this is using the same conventions.
Okay.
Yes, if you could email me the explicit expression, I'd be interested to just look at that and compare it explicitly. So when you take the t0 limit, right, as well.
Yes.
After you take the t derivative.
I mean just the coefficient of S squared t. So I think it is just what you have in left-hand side if n equals 1.
Yeah, I think I'd be interested to just take a look at the explicit expression and see whether or not the signs come from some convention.
Okay,
That might
I
be
have one
different.
more question. So when you derive the unitarity bound, I think for the non-fold limit, maybe previous slide. More. So I mean, we take the complete set. I mean, to insert complete set, and if we consider the multiple internal line, then
so we're not specifying any Feynman diagrams explicitly, right? As you're saying, we insert, just like here, for example, in the transition matrix element,
yes,
we can insert a complete set N here, which is some unknown UV matrix element, right?
Yeah.
But we don't need to know what this transition matrix element is explicitly to know that it has to be positive from unitarity. Because it just has to be a complete set by definition, right?
Yeah. I think in fold limit it is okay, but in non-fold limit, and you take the.
So there are extra steps here that I haven't made explicit, right? So when taking the T derivative, acting on this,
Yes,
we are acting separately in the partial wave expansion, and this T matrix element is already, in a sense, a partial trace that factors out the trace over these other quantum numbers, and then this T ket is, in a sense, defined to be including the traces over these UV matrix elements. So it's a similar steps. It's just done in more detail when you actually act the T derivatives on these parts. But I think your point is that it may not be as straightforward to insert a complete set of states when you're doing this in this beyond forward limit case.
I thought so, but yeah, let me think. No, let me think by myself. Sorry. Thank you very much.
So yeah, we try to be explicit in the paper, in the steps that are involved. But I'd be happy to discuss further if you want to email me and ask about this.
Okay, thank you.
Okay, further questions or comments?
Hello, I have a question on the. So in certain part of your talk, you consider m square going to zero limit in certain cases. So in this diagram, I wonder what happens when there is a massless mode like a photon plus electron in QED. Then the branch cut will start from the s equal to 0.
Yes.
In that case, how do you deform, etc.? And is there no problem?
So for the massless case, One essentially just regulates this by putting in a small mass, and then essentially it proceeds the same way, but we just introduce a regulator, and then
just I mean, you just assume some non-zero finite mass for the for example photon.
Right. So this is for the photon. I think this is okay, but for example, the graviton and constraints involved, gravity, there's more subtleties involved, I think. So yeah, this is a technical area for the gravity case, which I'm not so familiar with. But as far as I understand, regulating for the photon case is perfectly fine. And in the gravity case, where it introduces extra assumptions, which are not as straightforward.
I see. So in your case, you consider not only zero spin, but the general spin case, right? The massive spin case. So in general, if you describe this massive spinning particle in terms of the Lorentz tensor or Lorentz spinor, then you have to remove some a lot of non-physical degree of freedoms, which is also related with how you generate mass of these higher spin particles.
No, those are all included.
So so in certain part of your talk, you assume that your formalism applies only to the transverse polarization of the spin particle, for example.
We don't make any assumptions about which modes. We can specify any combinations of helicities, right?
So in your formalism, your formalism, the result does not depend on how you generate the mass for the spin 1 particle, spin 2 particle, etc.
No, because the amplitude is fully general. So we can specify constraints on any combinations of the helicity amplitudes as long as they satisfy this expression, right? So we sum helicities involved, but then these amplitudes contain all the degrees of freedom relevant for those amplitudes, transverse or longitudinal.
I see.
Yeah, but it's true that because we have to do this sum to get a positive constraint, it may no longer be the case that we have a constraint on just the longitudinal or just the transverse, but it has to be some combination. Unless one makes this assumption that this piece in the massless limit is negligible, in which case one could still place a constraint on the individual amplitudes. Yeah, but this is I think a key point that had been missed in the past.
So then in this case, you know that the one classic example for massive spin particle is W longitudinal WW scattering, W longitudinal W elastic scattering violating unitarity without Higgs boson, right?
Right.
So in your language, how does this happens? I mean, how does this show up in your formalism?
So this is a case where we don't get a constraint from the at dimension 6 and 8.
I see.
So this shows up in the formalism essentially by saying that the sign isn't constrained. Yeah. So we do have a vector example in our paper, which
I see.
Which explains this. So the constraints arises either by having a stronger assumption on the energy growth or by going to higher dimensions.
I see. And I have one more question. In general, some of the higher dimensional Wilson coefficient will be renormalization scale dependent, right?
Yes.
Then in that case, at which renormalization scale can you apply the positivity bound?
So that's an interesting question that has been discussed in some papers by Bellazzini and Riva. So I don't want to say anything wrong, so I won't say anything and just refer you to their discussion because.
Sorry, could you say again the reference?
So Francesco Riva and Brando Bellazzini.
I see.
And
Okay.
Riccardo Vettazzi. So in their latest paper on the positive moments, I think they, if I recall correctly, they had a section discussing RG constraints, or maybe it was a previous paper of theirs.
Okay, I see. Yes, thank you. Thank you very much for nice talk. Yeah.
Sure. Thanks for your questions.
Okay. Are there other questions or comments?
I can ask you just one simple question. So this is okay, I'm not following this story these days actually. But your statement is completely based on tutu scattering, right?
Yep.
And so if there are some operator which doesn't fit the tutu scattering, then there is no way to be constrained, right, in this way. So is there any like a effort to extend to maybe like a amplitude with more legs, like a 2 to 3, or is it possible?
So yeah, I asked Scott this because Scott's the expert who has a wide knowledge of anything positivity related, and he said, well, in the early, in the old days, 60s, 70s, and 80s, when people were first doing this, he sent me some papers where there was some work in looking at the analytic properties of amplitudes beyond 2 to 2, but it gets horrendously complicated. So I think there's the most recent paper is maybe one by maybe Clifford Chung or Grant Wemman, I can't remember. But I think they start looking at the analytic structure beyond, but you have to make many more assumptions, and it becomes very tricky. Basically, I think there's not much work because it's horrendously complicated, the analytic structure at that.
Do you have a reference number for this? The paper by Clifford Chung that you mentioned?
Yeah, I can email it to you when I find it.
Okay.
But yeah, the general. So yeah, I should apologize. I didn't really give any references or any survey of positivity work. So this is described in the introduction to our paper, but the generalizations that have been done tend to be more like. So we did 2 to 2 for a massive spinning case. The positivity moments introduces extra constraints that are order by order. So nonlinear constraints in a way that relate C6 to C8, C8 to C10, and so on, and really outline the shape of this space in. And then there's other approaches which use full crossing symmetry. So not just crossing symmetry between the S and U channel, but also T channel. So this can also give you extra constraints. And then there's been many papers applying these to phenomenology of colliders, for example, the SMEF with Nick Rudd and Grant Wemman, and then other papers that apply this to cosmology and effective field theories in cosmology and so on. So yeah, there's a big literature out there that's growing very quickly.
Okay, thanks.
Yeah, please remind me by emailing me if I forget to email them to you.
Okay.
Or have your student come and knock on me.
Okay, I wanted to ask about him, but maybe later. Okay. I'm done. Jayon.
Okay. More questions or comments? Okay, if not, we might thank Tevong again. Thank you.
Thank you very much. Thank you.
Anyway, hope to see you all in person soon.
Mhm.
Thank you.